All right, let's just dive right into this. Welcome to this explainer, where we take complex ideas and break them down into a visual journey. Today, we're looking at something totally fascinating. Think about it. We are entirely surrounded by machines that seem to think for themselves, right? They're predicting our needs, building our cars, even pouring our drinks. And honestly, they're often doing it better than we can. But what's actually running the show here? What are the invisible brains powering our modern world? Let's find out. Okay, wow, I know. This schematic is incredibly intimidating. If you're feeling a little overwhelmed right now, looking at all these buses, cores, and interfaces, you are absolutely not alone. This gives you a real sense of the true, raw complexity of a microprocessor. It basically looks like a map of a sprawling alien city. But don't worry, we aren't going to get bogged down in the engineering weeds today. We're going to make this incredibly simple. Because honestly, when you strip all of that crazy complexity away, this definition is all you really need to remember. A microprocessor is just a tiny brain. That's it. It's a tiny brain embedded within a machine that processes data to make that system smart, allowing it to operate without constant human input. It's the core technology that frees us from having to hold the machine's hand every single second of the day. So here's our roadmap for today's explainer. First, meet the invisible brain. 2, the sense, think, act loop. 3, teaching robots to work. 4, inside the bottling plant. 5, the cost of automation. And finally 6, the smart paradox. All right, section 1, meet the invisible brain. You know, it's wild how well these little chips scale in real-world applications. On one end of the spectrum, you've got massive, heavy-duty robot arms dynamically assembling a car chassis on a factory line. On the completely other end, you have a very simple sensory system precisely pouring liquid into a bottle. The physical hardware couldn't be more different, but the secret ingredient in the middle is exactly the same. That tiny brain, the microprocessor, is running the show for both. Moving on to section 2, the sense, think, act loop. So, how does a tiny piece of silicon actually interact with its physical moving body? Well, it's actually pretty beautiful. Every single automated system operates on a continuous rhythm that totally mimics biology. To interact with the physical world, machines follow the exact same logical loop that you and I do. Sense, think, act. Let's break that loop down step by step. First up, the machine has to sense. This is done using hardware like cameras, light sensors, or pressure pads. These are basically the machine's eyes and fingertips, gathering data from the physical world. Second, the microprocessor steps in to think. It analyzes that gathered information in mere milliseconds to figure out the correct response. Finally, the machine has to act. The tiny brain sends a signal to an actuator, maybe a motor, a switch, or a valve. These actuators are the machine's muscles, physically carrying out the response. Sense, think, act, over and over again. Section 3, teaching robots to work. Now, robots don't just wake up knowing how to build a car, right? They require explicit instructions. There are 2 primary ways humans teach them. First is direct programming, which is exactly what it sounds like. A human operator sits at a terminal and types out a highly precise sequence of computer code. But then you have manual lead-through, and this is actually super cool because of how physical it is. An operator literally grabs the robot arm and physically guides it through a task. The computer memorizes those exact physical movements so it can repeat them endlessly. It is literally muscle memory for a machine. Once the robot knows the movements, it needs the right hands for the job. In robotics, these are called end effectors. They're the specialized tools slapped onto the end of the robot arm. You might have a spray gun for perfectly even industrial painting, a welding gun for securely joining metal parts, or grippers for hauling heavy stock around a warehouse. The brain stays the same, the arm stays the same, but you swap that end effector and you completely change the machine's whole purpose. Okay, section 4, inside the bottling plant. Let's pick up the pace and zoom out a bit to the factory floor to witness a bunch of these invisible brains coordinating together in real time. Picture standing inside a high-speed bottling plant. We're not just talking about one robot doing one task anymore. This is a complex production line. It's a highly coordinated symphony of multiple sensors and actuators working in absolute perfect unison, all managed by microprocessors constantly communicating with each other. Watch how fast this cycle happens. Step 1, detection. Sensor 1 detects an empty bottle is in the exact right position. Step 2, filling. The microprocessor instantly signals an actuator to open the valve, pouring the liquid. Step 3, monitoring. Sensor 2 is watching that liquid height, and the absolute second it's full, the computer snaps the valve shut. Step 4, moving. The computer triggers a motor to advance the conveyor belt, bringing the next empty bottle right into place. And here is the real wow factor. That entire 4-step loop happens flawlessly 120 times a minute. 120 cans a minute. It vastly outperforms human speed, and it literally never spills a drop. It's a total marvel of efficiency. Section 5. The cost of automation. Let's take a breath and deliberately slow our pace down here for a second, because with that incredible efficiency comes some very real-world operational and labor impacts. Evaluating this objectively based on our source material, the advantages are undeniably massive. These machines work 24/7 without needing breaks, holidays, or sleep. They handle highly dangerous environments, extreme heat, harmful chemicals, keeping humans completely out of harm's way. But on the flip side, the disadvantages are substantial. You've got incredibly high initial setup costs, and if the power or computer fails, the entire multi-million-dollar line stops dead in its tracks. And, crucially, the direct replacement of human workers on these repetitive tasks often leads to localized unemployment. So it's a really complex economic trade-off. And operationally, the trade-off looks like this: absolute consistency versus total inflexibility. The crucial point here is that, yes, robots provide absolute consistency. Every single product manufactured is totally identical. But they struggle completely with unusual tasks. If a bottle is dented or falls over or literally anything happens outside their explicitly programmed sequence, the machine doesn't know how to improvise. They only excel at doing the exact same sequence, repeatedly. Which brings us to Section 6, the smart paradox. Finally, let's zoom all the way out from the microchip, past the robot arm, past the factory floor, and look at the profound societal implications of this technology. The promise of computer-controlled systems is wonderful, right? They make life fundamentally easier and safer by eliminating human error. But on the other side of the scale is the price. Convenience creates vulnerability. This is the paradox. The more capable the machine becomes, the more dependent the human operator becomes. So, what does that dependence actually look like in practice? Well, human operators risk losing their own basic manual skills because the machines just do everything for them now. Our total, unquestioning reliance on these invisible brains exposes society to massive new threats, like wide-scale system hacking that could legitimately shut down essential services. And as we constantly upgrade these microprocessors to be faster and smarter, we are generating massive, unprecedented amounts of electronic waste. Which leaves us with a critical thought to end on today. We've seen the sheer brilliance of the tiny brain, that elegant sense-think-act loop, and the unbelievable speed of an automated factory. But considering what we trade away for all that efficiency, you really have to ask yourself, is the convenience of a fully automated world truly worth the vulnerability of absolute dependence? Just take a moment to really think about that the next time a machine automatically does a job for you. Thanks for joining me on this explainer. I really hope it brought these concepts to life. Keep learning, keep questioning, and I'll see you next time.